Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
That's me. I want to be the universe's friend, and I believe I am. I am Dr. Moiya McTier, astrophysicist and folklorist and friend to the universe and to you. Who are you?
I am Corinne Caputo, a writer, comedian, friend to the universe. I feel like you, Moiya, are like the universe's hype woman. In like a fun way. You're like really like getting me on board with it.
Oh, that's what I aspire to be.
Yeah.
But I feel like I have to love the universe a lot to be its hype woman, and that's something that I struggle with sometimes.
Yeah, I get it. It is, I think anything that is fascinating and we've devoted our lives to gets, there's like the slumps of like, I don't know about this.
I'm going to be totally honest with you listeners. Today, I'm in one of those slumps. Today, I know that I am a friend to the universe, but I don't know if the universe is a friend to me.
Yeah.
I had a moment earlier today when I was preparing for this episode where I just felt real dumb. And I just, maybe that will help some of you feel better. You know, like I know that a lot of you think of me as a very smart person, and most of the time I am. But sometimes even the smartest people are like, wow, I know nothing. Because once you learn enough, you realize how much you don't know. And I was caught in that trap today.
Yeah. I know, I laugh because we can be so harsh on ourselves, but like, I never think of you as someone who's not smart. You just like, we all have our niches, and it's funny how I have the same self-talk sometimes, especially after a moment of being like super disappointed in myself. But none of us think that about you, Moiya.
Oh, thank you, Corinne. I gave the mean voice in my head a name, and its name is Carl. So earlier today, I heard myself say aloud, "Oh, I'm so stupid." And then I caught myself and I was like, no, Moiya didn't say that. That was Carl.
Yep.
And Carl, you suck. Shut up, Carl. And so I was screaming by myself in my apartment earlier today. Shut up, Carl.
Drag Carl.
Yeah, so sometimes if you have a mean voice in your head, give it a name and then you can tell it to shut up, and it usually works.
I love that idea. I'll have to think of a name.
But I kicked Carl out of my head and of this space that we're in because this space is too beautiful for any Carl or any of his kin.
You're telling me.
Right now, we are recording this episode in a peaceful bathhouse in the sauna room. There are naked people around, but I'm not letting that affect me and my ability to communicate science.
That's just all part of the universe, you know?
Yeah, it is. You know, their naked bodies, they are also space. And you can hear the gentle lapping of the water. You can smell the soaps in the air. It's a really nice, cozy spot.
I have to say the soaps at bathhouses and saunas, especially this one, are so much better than whatever soaps I'm using at home. I need to bring some of that luxury home.
Yeah. Corinne, I'm going to get you some better soaps.
Yeah, I know. I did look up finally like an Aesop soap. $45.
Excuse me?
I know.
You can make your own soap for less money.
You can get Dial for 89 cents.
Yeah. You could go buy a whale and render its fat and then make your own soap.
I could do it. I could do that. Yeah, crazy. But that's why we're here. We're treating ourselves to a luxury day.
We are. We deserve this pampering. Because what we're talking about today is not the easiest stuff to imagine and think about. So we wanted to give ourselves a little treat for thinking about today's topic, which is, little drum roll, the 4 fundamental forces of the universe.
What?
Can you imagine a sports announcer using their voice to talk about the fundamental forces of the universe? And then the crowd goes wild.
I think that'd be a really fun move for like a middle school science teacher to try.
That'd be great. I'm sure it's happened, and I would love to see it.
Me too. Show me that TikTok.
Yes. So modern scientists have identified 4 different forces that underpin all of the motion, all of the dynamism, all of the dynamicism.
Yeah.
Fuck, words are hard. Modern scientists have identified 4 fundamental forces that underpin all of the motion and like energy stuff in the universe. That's not to say that there aren't more, and actually that's not to say that there aren't fewer, really, because science is actively happening as we speak.
Wow.
Tomorrow they might come out with a different idea of the 4 fundamental forces. But right now, scientists are saying that there are 4 forces, and those are gravity, the weak nuclear force, the electromagnetic force, and the strong nuclear force. And that's in order from weakest to strongest, actually.
Whoa. Oh, gravity's even weaker than weak force.
Yes. This is what happens when we name things poorly in astronomy. It gets people confused.
Yeah.
So gravity, as the force that we are all most familiar with in our day-to-day life, it is actually the weakest of these 4 forces, which is surprising to a lot of people, including me.
That feels like naming documents and you're like final, or like final revised 2. Like, you just keep getting to the next or discovering the next thing and you're like, no, this one is the final one.
Yes, I did that with my dissertation files.
Oh my God.
I do appreciate that the strong nuclear force is the strongest of the forces. That makes me happy.
I do like that too. That makes sense to me.
But we haven't always known about these forces. The earliest of these was discovered in the 1600s. The latest of these was discovered in the 1900s. But before that, people observed stuff moving around in the world, but didn't know about these 4 forces. So they attributed it to other things. So first, in this episode, I'd like to take us through a little walk about the historical understanding of forces in the universe.
Let's do it.
So humans have always observed the natural world around us. That's how we survive. We have to see things and react to it to keep ourselves alive. But we weren't always trying to explain the natural world around us. Once we started explaining it, most humans, most of our ancestors did it with mysticism and with magic. Many cultures were animistic. Have you heard of animism?
Is that like animal? Is that related to animals?
Kind of. So animism was the belief that animals, as well as inanimate objects like trees and other forces of nature, had their own life force. That was very popular in a lot of pagan religions, and it's actually kind of coming back now with modern ideas of psychology and consciousness with the idea of panpsychism. So some modern psychologists would believe that every object, whether it's inanimate, whether it's sentient or not, has some level of consciousness.
Okay, that is, when my OCD is like really peaking, that's what I'm thinking in my head. I'm like, I can't pick out this can of beans because I would separate it from the other can of beans. It's like the Toy Story like thing of like everything comes alive when I'm not looking.
Yes, there you go. That is animism, that is panpsychism. So our ancestors who believe this would attribute the motion of those objects or anything that they do to maybe their inherent life force or to some supernatural deity outside of that object that was moving it according to their will. But we stayed there for several thousand years as a species. But then some 2,500 years ago, we started to explain these natural phenomena around us with math and base those explanations on first principles. So getting rid of the supernatural angle of it just based on what we can observe and what we know to be true in the world around us. How do we think this works? It's like the start of physics. It's the start of science, which is very exciting for me. There are a lot of people who would call the ancient Greek Thales or Thales, who lived in the 500s BCE, the first physicist. He believed that all matter in the world and in the universe was based on a single element, water. And that because they knew water had different phases, it has its solid ice phase and it has its gaseous vapor phase, that all of the different forms of matter that we see are different combinations of water in its various forms.
Cool.
Obviously, we know that's not true.
I'm like, in my head, I'm like, I buy it.
I know, right? I'm so gullible. If someone came up to me on the street and was like, everything's made of water, I'd be like, well, yeah, okay, sure.
I'd be like, of course.
But then there were, like, for several hundred years, there was this, I'd say, rampant debate about what the fundamental constituents of matter in the universe actually are. A little bit after Thales, there was a scientist, an early scientist named Anaximander.
Okay. That's a good name. That name's going to come back.
Right? Anaximander. We have Anaximander. There was also Anaxagoras in an earlier episode that we talked about.
Yeah.
Like, there are some good names in ancient Greece. So Anaximander proposed that there was another basic constituent of matter called apeiron.
Okay.
He didn't really say what that was. But then there was another person, Heraclitus, who countered that the only thing that really matters, that the thing that makes a difference between different types of matter is how they change over time.
Okay.
So he was one of the first people to bring in a time element, which is really important. And then it's in the 300s BCE, we are finally at the time of Aristotle, who added a bit more science to everything. A lot of people would consider Aristotle and Plato like the fathers of modern science and scientific thought.
Mm-hmm. That's definitely who I did like elementary school projects on.
So Aristotle and his contemporaries, the people who were around at the same time as him, they believed that everything, all matter, was made up of different combinations of 5 elements. And those elements, maybe you can guess most of them, Corinne.
I know this from Avatar.
Yes.
The Last Airbender.
Exactly.
Which is water, fire, wind, or air, I guess,
Air.
and earth.
Yes.
Yeah.
Yes, so those are the 4. And then the 5th would be ether.
Okay. A catch-all group?
Well, ether was the stuff outside of the terrestrial sphere.
Okay.
And so they believed that the Earth was all of these 4 elements arranged in like concentric spheres. So in the middle you had water, because water comes from under the ground. Like they have water tables. They would have known that. So in the middle you have water, then you have Earth, then you have air, because they're like, oh, we're breathing air, we're in the atmosphere. Then there's fire, which is what all the stars are. And then there's ether, which is like the stuff between stars. Between and beyond stars. And for them, motion was often seen as objects made of different elements trying to return to their own realm. So I'm quoting from this article that I found. A stone fell to the earth because it was trying to return to its own element, and flames rose because they wanted to return to the realm of all-enveloping fire, whilst smoke, a combination of air and fire, also rose towards the heavens because that's where the air and the fire realms were. Water flowed downwards because the realm of fire lay below the realm of the earth. And so this is what made things move, right?
That's pretty good.
They just want to go home. Things just want to go home, Corinne.
I love that. That's me.
Aristotle also believed that heavier things fell faster to the ground because they had more of an inherent quality called like heaviness or gravitas.
Ooh.
That word will come back later. But he was proven wrong by Galileo, who dropped things of different masses and showed that they're all accelerating towards the Earth, towards the surface of the Earth at the same speed. So Aristotle was wrong in so many ways.
Womp womp.
But this does take us to Galileo Galilei, one of the best scientist names, I think, in the history of scientist names.
Absolutely.
Yeah. And Isaac Newton. Both of them were around in like the 15 and 1600s, and they are very important in our modern understanding of gravity. So gravity, this is now the first fundamental force that we're talking about. It's the weakest of the 4 forces, and I'm going to go through them in that order from weakest to strongest. And this is also like roughly in order of how they were discovered too. So gravity was discovered first. A lot of people will credit Isaac Newton with the discovery of gravity, though he didn't discover it. You know, people knew that gravity was there. He was just the person who like thought about it the most and figured out how it worked. Kind of.
Yeah.
So Isaac Newton was an English mathematician who lived in the mid-1600s. He helped invent calculus, and he determined that white light was actually a combination of all of the other rainbow colors. So he has other claims to fame, but he is most well known for this legend of him discovering gravity because an apple fell on his head. Yes.
Yeah.
Oh, yes.
I know that story.
Everyone knows that story. And it did most likely happen. But there was a lot of work that was required after that for him to say, oh, hey, I discovered gravity. He was the person who called the force gravity after the Latin word gravitas, which means weight or weightiness. So Isaac Newton was admitted to University of Cambridge in 1661. He's a British boy. And 4 years later, the bubonic plague hit Europe.
Uh-oh.
He had just finished one of his degrees, but he was still associated with the university. Like, he basically finished his bachelor's and was staying on to do his master's or whatever. But when the bubonic plague hit, the university shut down.
Yeah.
We're all very familiar with this
I know that
now,
well.
unfortunately. Yeah. And so while he was in lockdown for the bubonic plague, Isaac Newton was sitting under a tree one day. He saw the apple fall, and he started thinking more in depth about gravity, following in the footsteps of Galileo and Aristotle and all the people who had thought about the force of gravity before him.
I think I remember seeing in COVID lockdown, someone like posted a thing of like, Newton discovered gravity during his lockdown.
Yes.
What are you doing? And I was like, we're surviving.
Exactly.
All we're doing right now is staying alive and loving on the people we love. And that's all we need to do.
That's all we need to do. People, yeah, I heard that too. People were like, Isaac Newton, he discovered gravity. He wrote his big magnum opus during lockdown. That part actually is not true.
Oh, good. Thank God.
Yeah. So the lockdown was from 1666 to 1667. Newton didn't publish his mathematical principles of natural philosophy, often shortened to Principia, until 1687. So for 20 years after this lockdown, he was working on figuring out how gravity worked. And in that big publication, in the Principia, Isaac Newton also laid out his 3 laws of motion. So those laws, the 3 Newton's laws, are number 1, the law of inertia, which says an object at rest tends to stay at rest. Have you heard of this?
I've heard of that one.
Yes. Number 2 is the law of acceleration, which gives us a beautiful formula that I have used to derive other formulas so many times. This is the force equals mass times acceleration
I love
equation.
that formula.
It's elegant. It's beautiful. I think, and this is just me speaking, I think it's even better than E equals mc squared.
I think so too. You know why?
Thank
it's
you.
accessible.
Yes. Yes. You know what else it is? It's accurate, because E equals mc squared is not the whole equation. We are,
Hell yeah.
when we say the E equals mc squared, we're totally leaving out the momentum factor of the equation, whereas force equals mass times acceleration, that's just the whole thing.
Yeah.
You can use that small 3-letter equation to derive so many force equations across different conditions. It's beautiful. So that's his second law. And then Newton's third law is the law of action and reaction. Corinne, do you have any idea what that might say?
I do know that one. That is any action has an equal and opposite reaction.
Yes, it's the equal and opposite reaction law. Thank you. So Newton, he published those laws. He was also one of the first to say that the force that pulls apples down to the Earth, so this gravity, is the same as the force that makes planets orbit the sun. And he was doing that largely based on Kepler's observation of planetary motion earlier in the 17th century.
That feels like a big connection.
Very big connection, yeah. Like, it's a big leap to go from, the thing that makes us fall is the same as the thing that keeps us around the sun.
Yes.
That's because, so Kepler made his 3 laws of Keplerian motion by studying the motion of planets around the sun, and also like the moon around the Earth and the moon around other planets. But he didn't know why that was working. And so Newton looked at Kepler's laws and assigned gravity to be the thing that made those laws work, and figured out that, when you add gravity to the equation, that is what's keeping the planets in place. Einstein added to Newton's theory of gravity in the 1900s with his theories of general and special relativity, which are still being tested and largely prove correct today. But we in the future will probably do its own episode on special and general relativity, because there's a lot up in there. The cool thing about gravity, there are a lot of cool things about gravity, but I think one of the most cool things about gravity, despite the fact that it is the weakest of these 4 forces, it is the force that operates on like the longest scales.
Okay.
So gravity can operate at infinite scales, pretty much, because it is just an inherent quality to anything that has matter. If you have two things with mass, no matter how far apart they are, they will feel some type of gravitational attraction. Of course, if they're super, super far apart, the attraction between them might be so low that it's basically negligible, but it's still there.
Yeah, I love teaching that to kids at the Space Center, of just talking about how like anything with mass has gravity, because we have this really fun like true or false game where like it ended on like people have gravity, true or false, and everyone was like, no. But then we got to be like, we do, but like we don't, it doesn't even matter because everything else is so much more massive. But that was so fun.
I love that. Little kids
really cute.
realizing that they have gravity. You have mass, you have gravity, you matter.
Yeah, that's so cute.
So the big equation that Newton came up with to describe the force of gravity, aside from mass equals acceleration, this is F equals G times the two masses multiplied together over the distance between them squared. And G that I said, that is a constant. That is what we call the gravitational constant, which is this factor that can be used to scale the force of gravity. It does have a value, but that value wasn't determined until almost 100 years later in an experiment by Lord Henry Cavendish, who experimentally derived the value of this constant that Newton put into his equations. Cool stuff. Any questions or thoughts on gravity before we move on to electromagnetism?
I love gravity. I don't think I have any questions on it. I just think it's my favorite. We'll see.
Yeah.
We'll let the others impress me, but...
Yeah, I'm wondering if this is just what's it called? The mere exposure effect, where you know gravity really well, so maybe that's why it's your favorite.
That's absolutely what it is.
Yeah, let's get you understanding the other forces a bit, and then you can tell me what your real favorite is. So the next force is the electromagnetic force. If gravity acts between any two things that have mass, then the electromagnetic force acts between any objects with an electric charge. And this force is, if I had to describe it or like summarize it in a short phrase, it would be opposites attract. The electromagnetic force is the one responsible for opposite electrical charges attracting and like electrical charges repelling each other.
Okay. Okay.
So this is actually split up into like two different types of forces that scientists thought were separate, but then realized that they're actually the same thing. And that is the electric force and the magnetic force. Because we had observed them separately, but it wasn't until the 1820s that we realized they're actually the same thing. So the electric force happens between static charged particles, so charged particles that are not moving, whereas the magnetic force operates between charged particles that are moving. And since you can use a magnetic field or an electric field to produce the other, they're essentially the same thing. So in 1820, a scientist named Hans Ørsted showed that magnetic force and electric force are connected because a moving electric charge generates a magnetic field. And if you have a magnetic field and you put a conductor through it, that will also generate an electric charge. So you can go from one to the other, which we didn't realize until the 1820s.
Okay.
Electromagnetic forces operate on also pretty long distances because they are carried by the photon, which is the particle of light, and that has no mass and it has no electric charge, so it can just fly through space. But it also operates best on short distances. So it's weird because you can carry electromagnetic energy across the entire universe in a single photon. But for this opposites attract thing to work, you have to be close enough for those charges to actually come in contact. And so the electromagnetic force is responsible for generating light, which is also known as electromagnetic radiation. So that's the connection there.
I know that one.
And it's why we don't fall through chairs and other solid objects, or like really, like it's what keeps us separate from everything that is not us. So I remember in high school learning about the fact that because our entire body is made up of atoms and atoms have electrons on the outside, anytime you touch something else, the electrons that are your body are repelled by the electrons on the outside of their body, or like anything. So you're in chemistry class, our teacher told us that we are never actually touching anything. And one of my friends reacted to that by saying, well, I just don't trust science because I know I touch things. And you just told me that science says I don't touch things.
Yeah, well, so that can't be true.
This is why people need to be really careful when they just say cool scientific facts. Like if they don't tell you the nuance, if they don't tell you how or why things work, people walk away from those little factoids with inaccurate information. So I really hope that friend of mine trusts science now, especially because she is an elementary school teacher. So, so that's electromagnetism. It's also why you asked once, I think, in an earlier episode when we were talking about dark matter, if we could touch it. And the electromagnetic force is why we couldn't touch it, because dark matter only interacts with gravity. It does not interact with the electromagnetic force, which means we could not touch it.
Oh, interesting.
That's like how our touching works. Mm-hmm. So it's why we don't fall through chairs, which makes me think that maybe ghosts have like a selective interaction with the electromagnetic force, because they can sometimes walk through things, but they don't like fall through the floor.
Okay, I made a web series about ghosts years ago, which is online if anyone wants to see it. But one of the rules we established for these ghosts is that they can go through anything but glass, which we made up randomly. But I think it's actually in an X-Files episode too. But that was one of the things we decided ghosts couldn't do. I mean, we also walked around, but we specifically could not manipulate glass.
Nice. Was that because the glass would just reflect you? Like, what would happen if you tried to go through glass?
I don't know if we had a justification for it, but what happened if we touched the glass bottle was we were moving it the way a person would. So hypothetically, in this universe, we could have picked up a glass cup and carried it around a room and then scared somebody.
Interesting.
I don't think it ever affected the plot. If I rewrote this series now, it would have a purpose.
It must. You just left Chekhov's glass.
I know.
Sitting on the table.
Season 2. Let's go.
Hi, it's Corinne, here to give a shout out to our amazing patrons who are supporting this podcast. Thank you, as always, to our Sun-like stars, Sharn Llewellyn, Finn, and Ian Williams. And thank you to our latest Red Dwarf stars, Riley Oliver and Sarah Callahan. You too can support us, hear your name on this podcast, and make it to our patron star chart, all by supporting us on Patreon. Find the star chart, Patreon info, and more at our website, palebluepod.com. Or go right to the source, patreon.com/palebluepod.
Hey friends, is there enough queerness in your life? Probably not. There can never be too much. So I have a podcast recommendation for you to get more queer stuff in your brain. The Queer Movie Podcast is appropriately named. It's a queer movie watch party hosted by Rowan Ellis and Jazza John. You can join them every other Thursday as they research and rate their way through the queer film canon one genre at a time, from rom-coms to slashers to contemporary art house cinema to black and white classics. Queer Movie Podcast is a celebration of all things super gay on the silver screen. Or maybe just a little gay. I don't know. Whatever level of gay floats your boat, they're talking about movies that have that level. So every other Thursday, go to your favorite podcast app or to queermoviepodcast.com to listen to the Queer Movie Podcast. Thank you to BetterHelp for sponsoring this episode. I've actually struggled with anxiety and depression for years. I've been in and out of therapy. I've been on and off meds. And I know that when you're in the depths of one of those depression or anxiety spirals, when you hate yourself and the world, that one of the hardest things to do is pick up a phone and have a consultation with a therapist and then go to their office and meet with them in person. That's all so difficult. But luckily, with BetterHelp, which is the world's largest therapy service, you can do therapy 100% online. With BetterHelp, you can tap into a network of over 25,000 licensed and experienced therapists who can help you with a wide range of issues. To get started, you just answer a few questions about your needs and preferences in therapy, and that way BetterHelp can match you with the right therapist from their network. And if you ever feel uncomfortable with a therapist, or if you feel like it's not a good fit, you can switch very easily for no additional charge. With BetterHelp, you get the same professionalism and quality that you would expect from in-office therapy, but with a therapist who is custom-picked for you, and there's more scheduling flexibility, and it's at a more affordable price. But to make it even more affordable, you can get 10% off your first month at betterhelp.com/palebluepod. That's betterhelp.com/palebluepod. So head to our link to join the millions of people who are making the really brave decision to improve their mental health. Again, our link is BetterHelp. That's betterhelp.com/palebluepod. Now we can move over to the weak nuclear force.
The weak.
They did these forces dirty. I would
They
be
really
so
did.
mad if like I had a twin and they were like, that's the weak twin
That's
and
the
that's
weak
the
one.
strong twin.
I do have a twin, and I am the weak one. And that's fine.
Corinne, do you actually have a twin?
Yeah, Moiya, we've definitely talked about this. I have a twin brother.
Oh, I forgot.
Who
I have
listens to the
forgotten about
podcast.
this.
Hi, Tom.
Hi, Tom. I totally forgot about this.
I don't think we look
Wow.
alike. I guess we kind of look like siblings. He's taller than me. He's blonde. He's great, but we're not. He's definitely stronger than me. No doubt about it.
Well,
But I will fight on camera for the Patreons. No, I'm just kidding.
I'm saying, if it's physical strength, yeah, I'm like, maybe he's stronger than you, but if it's comedy muscles, Corinne,
Yeah. He's very funny too.
you've got him. No, in my headcanon, he's not.
He's very good at, he's an engineer, so it's a right brain, left brain kind of twinship.
Okay. Interesting. Twins are so fascinating. Some stars are born as twins.
I read a book called Binary Star, and it was like a fictional book, but there were paragraphs explaining that. I have no idea if it was true.
Well, we can talk more about that in the next episode about stellar types. That's a hint. That's more than a hint.
An Easter
That's
egg.
just me telling you. Yeah, that's what the next episode is, friends.
Get excited.
Okay, so the weak nuclear force. I refuse to believe that you are the weak twin, Corinne. So this is not you. This is the Tom force, and the weak nuclear force is responsible basically for changing particles into other types of particles. Because we've talked about this on the show before. Space is dynamic. The universe is constantly changing on big and small scales. And one of the types of changes on small scales is that particles can just spontaneously turn into other types of particles.
That might be, I might declare that I'm the weak twin after hearing that, because that does seem like a superpower I want.
It is very cool. So in the 1920s, Enrico Fermi, who we talked about with the SETI episode, the namesake of the Fermi paradox, he was studying radioactive decay of elements. It was mostly for gross bomb reasons. Remember, he was very instrumental in building the nuclear bombs. But that did lead to the discovery of the weak force, which was originally called Fermi interaction.
Well, he's dragging himself with that.
Ooh, maybe they changed the name to weak force instead of Fermi interaction after he had like a real bad day on the basketball court or something.
That's exactly it. He actually bet the name of the force and lost.
We're going to say that's truth now.
Anything on this podcast is true.
Everything. We call it the weak nuclear force because Enrico Fermi made a very bad bet about his physical ability in a basketball game. Yes, so the weak force, formerly known as Fermi interaction, acts only on very small scales. And when I say small, I mean like the size of atomic nuclei, because it works within an atomic nucleus. So atomic nuclei are made out of protons and neutrons. That's what's in the nucleus, and then you have electrons on the outside. An electron is a fundamental particle. You cannot break it down into any smaller bits. But protons and neutrons can both be broken down into their building blocks, which are called quarks. Quarks themselves are fundamental particles, meaning there's nothing inside them. It's just a quark. You can't break it up into any smaller bits. But there are different types of quarks. Physicists and other scientists who deal with particles, they have assigned quarks 6 different flavors. Those are up, down, strange charm, top, and bottom.
Okay.
Hank Green has a really fun song that I used to study for the physics GRE when I was a senior in college. It's called Strange Charm, and it explains the different flavors of quarks. So yes, there are 6 flavors, but all of those flavors of quarks can also come in 3 different colors of quarks: red, blue, and green.
Whoa, that's a lot.
Mm-hmm. So I guess in total there are what, like 18 different possible ways that a quark can exist. But mostly we just talk about the flavors here, and the most common flavors of quark are the up and down quark. They are the least massive types of quarks, and they are the most stable. So strange charm, top and bottom, they usually don't survive for very long amounts of time.
Mm-hmm. To be named Charm in a science context.
I would love to have been a fly on the wall in that meeting where they decided what to call these, because why?
I know.
Why? So up and down quarks are the most common. They have different charges and slightly different masses. So up quarks have a positive 2/3 charge, whereas down quarks have a negative 1/3 charge. And if those numbers stress you out or like cause your mind to go cloudy, just forget about them. Just forget about them.
Done.
What you need to know are that protons and neutrons, they're both made of 3 quarks, but different combinations. So a proton is made of 2 ups and 1 down. And the reason I said those charge values before is because if you add up the charges of the quarks in a proton, 2 ups plus 1 down, you get 1 positive charge.
Okay.
Because it's 2/3 plus 2/3 minus 1/3, which is 1.
Okay.
Neutrons are made of 2 down quarks and 1 up quark. So that, if you add it up, is a neutral charge because it's minus 1/3 minus 1/3 plus 2/3.
Okay, so 0.
Yeah, so there's 0 charge. The weak force works by flipping the quark flavor in one of these particles. So in a proton, if it takes one of those up quarks and flips it to a down quark, that proton is now going to be a neutron. Except there are rules in the universe and in physics about maintaining or conserving electrical charge and mass and energy. So if you take a proton and you flip a quark and you turn it into a neutron, you've taken a positively charged particle and turned it into a neutrally charged particle. That doesn't work. That doesn't balance out. So you also need to produce an electrically negative charged particle, like an electron. So in all of these reactions that are fueled by the weak nuclear force, you get a proton that turns into a neutron plus an electron and like a neutrino or something. Mm-hmm. The opposite can also be true. You can take a neutron and turn it into a proton, but then you have to generate byproducts that balance everything out.
Okay.
This also works on electrons. I said that the electron is a fundamental particle, meaning it can't be broken down, but it can be manipulated. So the weak nuclear force, when you take the electron and you combine it with other things, can also generate other things like an electron neutrino or a proton. So the weak force takes particles, turns them into other particles, and generates byproduct particles.
That's a lot of work for a weak force.
It is, which is why I think it's a terrible name.
Maybe it's trying to lay low. Maybe it wants to be called weak force. It doesn't want you to really look too hard at it.
Do not perceive me. I am just the weak
Exactly.
force. I'm not doing anything over here.
Exactly.
Why is that the voice of the weak nuclear force?
No, that's definitely the voice of the weak force.
I actually didn't realize this until I was well into my career as an astronomer. I had always heard that it's the strong nuclear force that's responsible for nuclear fusion in the cores of stars. But now I know that you also need the weak nuclear force, because when you take atoms and you're fusing them together, they also need to change to become a new element, and then there are going to be a bunch of byproducts. Mm-hmm. Usually in the cores of stars, when you're getting nuclear fusion, the byproduct is like a neutrino and a photon, because that's what makes stars hot and bright and shiny.
Beautiful.
Mm-hmm. So we need the weak nuclear force to do fusion, but we also need the strong nuclear force, which is what we're talking about next.
Yes.
Any thoughts, questions about weak force?
Not one. No.
You know everything.
I think I'm an expert on it now. Nothing's coming to mind, but I think I have a good grip on what it does, and I do agree that the name is not quite right.
Yeah. Like, that's a great superpower. It's a transformative superpower, which is really cool. That's what I would want.
I feel like these were named in relation to each other instead of, like, in their independent abilities.
Yeah, they were. Because both of these nuclear forces were discovered very much around the same time.
Okay, that makes sense.
So the strong nuclear force is the strongest, and it's the force that operates on some of the smallest scales. The strong nuclear force will not work on scales larger than an iron atom, which is one of the reasons that nuclear fusion in the cores of stars will not make elements heavier than iron, because like the strong nuclear force kind of just stops working at that scale. There are other reasons too, like by the time you start fusing elements heavier than iron, that actually requires energy instead of producing energy. So there are a few reasons, but one of them is that the strong force, it means teeny tiny scales. So this force is responsible for holding atomic nuclei together, because in the nucleus of an atom, you have protons, you have neutrons. But if you remember back to the electromagnetic force, like charges repel. So it should be really difficult to get a bunch of protons smushed together in a small space. They should all be repelling each other. And they do. But the strong nuclear force is so much stronger than electromagnetic force that it can overcome the repulsion between them and hold them together. So the strong nuclear force holds them together with a particle called a gluon, which I think is one of the most appropriately named things in all of science. It is a particle that glues and holds stuff together.
Absolutely. It also sounds like something I would like go get at Michael's. Be like, I need to go, like, I'm working on this project this weekend. I'm all out of gluon.
Yes. That's the special high-powered glue that like NASA developed, you know?
That I use for like doll houses.
The strongest fucking dollhouse on Earth. So the strong nuclear force was theorized in 1935 by a Japanese physicist named Hideki Yukawa. But the how of the strong nuclear force wasn't discovered until the 1970s, when they learned more about the nature of quarks. And the reason I mentioned the quark colors earlier was because they are important for the strong nuclear force. The weak nuclear force has to do with the flavors of quarks, but the strong nuclear force has to do with their color. Ooh. There are 3 different colors, and they have to be balanced. So let's say a proton is made of 3 quarks, 2 up, 1 down. It will also have a red quark, a blue quark, and a green quark. Gluons and the strong nuclear force will spontaneously, I think that's the word, change the color of a quark, and it'll change the colors of all the quarks so that they are balanced. And a weird thing about the strong nuclear force, unlike the other forces, is that if you try to pull these quarks apart, the further the quarks get apart, up to a limit, the stronger the strong nuclear force is. It's kind of like a rubber band.
That's what you want out of glue.
Yes.
That's what you want out of glue.
Yeah. So if you connect 2 things with a rubber band, as you pull them apart, the rubber band is working harder to pull them back together, and that's kind of what the gluon is doing. It's really working to
really
stick
hard.
this stuff together. Yeah. So that is the strong nuclear force, which we didn't understand very well until the 1970s.
Recent.
But we were thinking about it for like 40 years before that. So all of these forces that I'm talking about are part of, or can like in some ways be explained by, the standard model of particle physics and quantum field theory.
Of course.
Of course. So the standard model of particle physics says that there are broadly 2 types of particles. There are matter particles, which are fermions, like quarks, and leptons, which are like electrons. There are so many types of particles, but broadly speaking, there are matter particles that give stuff like substance. Okay. And then there are force carrying particles, which we call bosons. Have you heard the word boson before?
It's ringing a bell. I don't know what it is.
Yeah, several times over the last 25 years, there have been brief spikes in the word boson being used in media, mostly because of the Higgs boson particle.
Yes, that's what I know.
A lot of people, I remember in the 2010s, were really trying to find the Higgs boson particle, which they called the God particle, because the Higgs boson, this force-carrying particle, we believe is responsible basically for giving objects their mass, or at least giving fundamental particles their mass. According to this model, each of these 4 fundamental forces should be carried by one of those bosons, by one of those force-carrying particles. So the electromagnetic force, we know, is carried by the photon. The weak force is carried by both the W and Z bosons. There are 2 types, which is probably a holdover from a time when we thought that it was 2 separate forces, electric and magnetic forces. And then the strong force is carried by the gluon. Again, the most appropriate name in all of science. We have not yet found a force carrier for gravity, and we're trying to. If we did, we would name it the graviton, which I think is also pretty appropriate. But the fact that we haven't found it yet is confusing a lot of people and is encouraging the search for what people are calling the grand unified theory.
Yeah. That, especially because gravity feels so prevalent and has been thought about the longest.
Yeah. And it's why is this thing that we are most familiar with?
Yeah.
Why is it also the weakest of these forces, and why is it the only one that we can't explain
we don't have
with
answers
one of these
for? Yeah.
particles? Yeah. So gravity is messing a lot of our models up, which is why we're coming up with new theories of gravity, while we're also simultaneously over and over again proving Einstein's general and special relativity correct. Gravity is causing a lot of drama in the sciences, is what I'm saying.
A gravitas?
Ooh, I love that. A little wordplay. So the Standard Model is part of quantum field theory, which is the way that most scientists today try to explain all the particles and forces and matter stuff that is going on in the universe. According to quantum field theory, particles aren't tiny little balls that exist independently of everything else. They're not physical spheres going around the universe. Instead, according to quantum field theory, particles are spikes in an energy or quantum field.
Okay.
Yeah. So I can see the confusion on your face. I get it. I have never taken a quantum class. I'll be very upfront about that. But this is the way that I understand quantum field theory. For this, I am actually going to be reading from my book, The Milky Way, an Autobiography of Our Galaxy, because I was very proud of the way that I explained quantum field theory in the book. So let me read it for you. Each of these particles is just a long-lived, discrete energy spike in its own so-called quantum field. I feel the need to stress that these are not actual physical fields that you can directly manipulate in any way. They're a convenient and constructed mathematical arrangement, a hypothetical medium for transferring different types of energy around the universe. It might be easier for you to think of these fields as software programs running on the back end of the universe. There's a program or a field that describes and controls electrons, a program for muons, another for inflatons, another for gluons, and so on. These programs rely on each other, so they interact in a way where, if you change or perturb one, it may or may not affect one or more of the other programs. Switching back to your scientist's language, they would call these interdependent software programs coupled fields.
I love that.
Yeah. So each of these fields determines the placement and the direction and the motion and the behavior of a type of particle. And they can interact in different ways. So when people call the Higgs boson the God particle because it gives other particles their mass, what they're saying, according to quantum field theory, is that the Higgs field, when it interacts with the electron field, for example, it interacts less strongly than it does with the quark field because quarks are heavier than electrons.
Okay.
So like if a particle is heavy, it interacts very strongly with the Higgs boson field. And you can do that between all of the fields for all of the particles.
Cool.
Does that make sense?
I think so. Like, electrons and quarks are these fundamental pieces. That's not the word.
Yeah.
And they interact differently with these fields based on how heavy they are.
Not just on how heavy they are. That was just one example.
That's one example, everybody. Don't quote me.
Right. It's so these electrons, these quarks, every single type of particle, according to this theory, is in itself one local representation of the larger field. So there's an electron field, there is a Higgs field, there's a quark field. And the quark field can interact with the electron field. The electron field can interact with the muon field, and so on and so forth. And the different types of interactions determine their behavior.
That I get.
Word.
That's kind of how I interact with, like, different friend groups or, like, different family or friends.
Yes. And you might have some friends, like, in different friend groups who you know can interact well with each other.
Yeah.
But you might also have some separate friend groups who you never want to mix because they don't interact well together.
And that's why bachelorette parties are chaos. Because every field is coming together.
Stay tuned, because coming from Pale Blue Pod is a treatise on how the bachelorette party is just the real world example of the quantum field theory.
If we see the eclipse in Austin, we, like, also interview these bachelorette parties that are there.
Oh, so many of them, and they're on that bus that also has bike pedals.
Okay, they're all over Portland, Maine too in the summer.
Like, why?
It's kind of chaos.
I don't get it. Are they actually doing the work, or is it motorized?
I think you are doing the work, which is why I never want to do it.
That's too much. That's
I'm
exhausting.
Not here for that.
No, thank you. So the reason I went into that long explanation of quantum field theory, maybe too long, is because understanding these particles as interacting fields makes it easier for us to compare their strength, which is why we're able to say something like gravity is so much weaker than the strong nuclear force, because they're totally different things. It would be like saying an apple is, I don't know, wetter than an orange, or an apple is louder than an orange. Like, what does that even mean? And so instead, you can come up with these coupling constants for each of these different fields, which is a measure of how well it couples with other fields. And the strong nuclear force, the gluon, couples very strongly with other fields.
Yeah, I buy that.
Much more strongly than gravity, which we don't even have a particle for. So those are the four fundamental forces, and like roughly how we think of them in terms of particles, but also as fields. Remember that light can be a particle and a wave, so all particles can either be particles or just spikes in an energy field. Why not? There might also, Corinne, be a fifth fundamental force. So this would be kind of like the antithesis to gravity, where gravity is an inherent quality of matter. If you have mass, then it will attract other mass towards it through gravity. There might be a fifth fundamental force that is inherent to the absence of matter.
Ooh.
A repulsive force that is inherent to the absence of matter called quintessence. Which might be what dark energy is.
I would love that.
We still have a lot more observing of dark energy across long time and distance scales before we can say whether it's this quintessence, but that is one of the hypotheses for what dark matter could be. Like it'd just be basically like the anti-gravity is already a word, but quintessence is even more anti-gravity than whatever you're thinking of as anti-gravity.
Yeah.
Because gravity is like mass will attract, and quintessence or dark energy might be the absence of mass makes things move apart.
Ooh.
We don't know yet.
We don't know. Wow, I can't wait to find out.
I know. So those are the forces, Corinne. How do you feel? What are you thinking?
I think there's a lot going on that I'm not aware of.
Yes, there's a lot out there.
But I do think gravity remains my favorite.
Okay.
Just because it's what I'm dealing with every day.
What do I like? I think I gotta go electromagnetism because,
Ooh, yeah.
you know, I am an astronomer, and up until 2015, all of the information we had about the universe was gained through the electromagnetic force, because it was light. But then in 2015, we saw gravitational waves for the first time. So we started getting information through gravity. So yeah, I'm okay with our collectively two favorite forces being gravity and E&M.
It's funny that neither of us are like weak force for the little guy.
Although if I had to, so like if we were to take all of these forces and turn them into superpowers, where, you know, like E&M, it makes stuff glow, and gravity makes stuff stick to each other, and well, so does the strong nuclear force. So many of these forces make stuff stick to each other, but the weak nuclear force is the only one that like turns things into other things. That's definitely the cooler power.
It's an incredible power. Yeah, it's a really good power, and that is definitely the power I'd want. That would solve all my problems. Like, I could turn this water bottle into, like, spaghetti. Like...
That's what the alchemists were trying to do. The alchemists were just trying to tap into the power of the weak nuclear force before they knew what it was.
Yeah, that's all.
That's it. So Corinne, what funtivity do you have planned for me today?
Okay, I have a little funtivity, and we can do it quick. But it was me coming up with other famous 4 forces.
Ooh.
And seeing if we can guess the names of the 4. And then if we want to do a bonus, if you could pick a 5th mystery one, you can. Okay, so this one we already did, which is from Avatar: The Last Airbender. There are 4 bending arts.
I believe pretty strongly that I would most likely be an earthbender.
I see that for you.
Thank you, yeah.
I have no idea what I would be. I think I would end up being like fire. Like, it would be something that I don't want to do. I don't think I'm a fire person.
I don't think of you as a fire person either.
Maybe water.
I can see that.
Or air, but I feel like that's claimed.
What? You could be an airbender. Why
Maybe
not?
air.
They need to repopulate anyway.
All right, there is the last one, so they might need another.
Yeah.
Okay, the 4 forces of flight, which we talked about at the Space Center a lot.
Oh.
For a plane.
Forces of flight, like,
what are the 4 forces that work together and keep this plane in the air?
oh, like, lift?
Lift, exactly. The next.
Oh, okay.
Lift. And then one we talked about today.
Gravity.
Yeah.
Okay, cool.
And then think of lift as like the arrow going up and gravity as the arrow going down. There's also an arrow going like left and right.
That's not pitch and yaw, is it? That's like the motion.
No, that's that's the motion of the plane, but like the one going towards, let's imagine like a 2D plane, the arrow that would be pointing to the back of the plane starts with the D.
Drag.
Yes. And then the arrow pointing forward starts with a T.
Thrust.
Yes.
Oh, cool. I was going to say propulsion until you said it starts with a T. Okay, cool.
Those arrows are just like for me to conceptualize it, but like it's lift, thrust, drag, and gravity.
Wow. Great clues.
Yeah. Thank you.
Thank you.
Okay, and then there are 4 Ninja Turtles, Moiya.
Okay, I know they're all like Renaissance artists.
I can give you the first letter again.
No. Let me try that. I know there's a Donatello.
Yes.
I know there's a Michelangelo.
Yes.
Leonardo.
Yeah.
Raphael.
Yes, that's it. The 4 Ninja Turtles.
You can't see it, listeners, but I'm doing such a happy dance.
Okay, and then this is there are 4 Jonas Brothers.
No, there's not.
There are 3 main ones, and there is a 4th little brother.
That poor 4th Jonas brother is like the 3rd Hemsworth brother that no one cares
Jonas
about.
brother.
Okay, well, I know there's Nick, there's Joe, and Kevin.
Yes, that's
I
the
know
3.
about Kevin.
That's the 3.
Okay, so just another white dude name. I don't know, like a Mark.
Very, like, no, but that is, you're in the right realm of thinking of, like, generic white names. Okay, not that you would know this. Starts with an F.
Frankie.
It's
Frankie Jonas?
Frankie Jonas.
That's a bad name. I don't like it.
Well, those are the famous 4 forces that aren't in science, besides the flight.
That's amazing.
I will say the first question I thought of for this little game was the Jonas Brothers, and then I had to go back and think it was kind of sort of science.
I think you did a great job.
Thank you.
That was really fun. I'm really proud of myself for knowing all of the Ninja Turtles.
You're so smart, Moiya.
Thank you. Thank you. Fuck you, Carl.
Yeah. Carl Jonas is the fourth brother.
I don't know if it's important for anyone, but it is Carl with a K. The mean voice in my head is Carl with a K.
Because I was just thinking that maybe my mean voice should be called Karen because Corinne is so often pronounced as Karen, like at Starbucks. And I'm like, oh, my name's Corinne. And they spell it like K-R-I-N. Mm-hmm. So maybe that's my alter ego.
Oh, I love that.
We already hate her.
Yeah. Fuck you, Carl, and fuck you, Karen.
Yeah, exactly.
I'm so sorry to any Carls and Karens in the audience. We are not talking to you unless you happen to be living in our craniums.
This has nothing to do with you.
Absolutely not.
Unless you're evil.
Mm-hmm. And whether or not you have any sort of voice occupying your head, remember that you are space. Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.